Students, we are going to do the conformational analysis of butane today. Butane has 4 carbons and 3 carbon-carbon bonds around which we can study the conformational isomerism. Now, if we study it using 1, 2 or 3, 4, we'll not be able to get many different type of interactions. It would be similar to the one which we have studied in propane. But if we study the conformational analysis, keeping our focus on C2 and C3 bond, then we will get to know how the two methyl groups are going to interact and how would the different conformations have different energies and all those things. So what we are going to focus on, we are going to focus on the second carbon and the third carbon. If you look closely, then both the carbons are connected to 2 hydrogens and 1 methyl group. So is the case with this one, right? So if I say that this is my C2, it is connected on one side by methyl and on the other 2 sides by hydrogens. And if I focus on my back carbon represented by this circle, it has 1 methyl and 2 hydrogens, fine? And I have depicted the first conformation as the anti-conformation, but you can start with any of the conformations from which you want to like I started with where the bulky groups are as far apart as possible, like 2 CH3s are totally anti or opposite to each other, right? This conformation is called anti-conformation. If I rotate this by 60 degree, keeping the front carbon fixed and moving the back carbon, then this hydrogen will come here, which you can see it's coming there. This methyl will go there, which you can see in the next structure is here. This hydrogen will go here, you can see it there. This conformation is an eclipsed type of conformation, but it is not fully eclipsed. Why? Because hydrogen is eclipsing CH3 or CH3 is eclipsing hydrogen. So it is like a small thing is eclipsing a big thing, or a big thing is being in the front and a small at the back. So it is a partially eclipsed type of conformation, right? So we have anti, we have partially eclipsed. Now if I rotate this by 60 degrees, this hydrogen would come here while this one will come here, and you can see hydrogens are coming there and this methyl is going to take this place. So methyl is going to take this place. This particular conformation is staggered, like the things are as far apart as possible, but it's not totally staggered because 2 bulky groups, they are quite close to each other. They are not totally opposite to each other, but they are in space close to each other. So although it is staggered but not completely staggered, such a conformation is called gauche. This is a gauche conformation, right? Now, if you rotate this conformation by 60 degrees, this hydrogen would come here, methyl will come here, and this hydrogen will come here. So methyl is going to now cover the methyl. So we get this type of conformation, which is an eclipsed conformation, and it is a fully eclipsed conformation because the 2 big groups, they are covering each other. Similarly, 2 hydrogens are eclipsing each other. Now, if you give it a further rotation by 60 degrees, so your methyl will come here, your hydrogen will come here, and the hydrogen will come. So 2 methyls in the gauche type of conformation, which would be similar to this. So there are only 4 extreme conformations in terms of energy and stability in case of butane when we do the rotation around the carbon second and third, right? Now let's look at these from the perspective of energy and all those stability type of the things. So in the first conformation, which I have depicted here, is anti or anti the 2 methyl groups, which are bulky groups of all the groups present in this molecule. They are as far apart as possible. So they are not going to have any torsional strain or steric strain. So this conformation is of lowest energy and thereby it is of highest stability, right? And if you look at the fully eclipsed conformation, these 2 groups which are bulky, they are very much close to each other. So not only their electron clouds are repelling, leading to torsional strain, but also there would be steric strain, like the actual physical bumping of groups into each other. So this would be of the highest energy since the groups are too close to each other, and those groups are, it also involves the bulky groups coming close to each other. So fully eclipsed is the most energetic and least stable. Anti or anti is the most stable and least energetic, right? Now let's look at the partially eclipsed and the Gauche conformation. In case of partially eclipsed, since there is an eclipsing thing which is happening leading to torsional strain, right? Groups are very much close to each other. So this is of higher energy as compared to Gauche, where the groups are far apart. They're far apart. So yes, there are interactions because the bulky groups are almost 60 degrees closer to each other, but it is always less energetic than the partial eclipsed where they're so close to each other. So the energy would be anti is having the least energy, and followed by Gauche, followed by partially eclipsed, followed by eclipsed. So this is, I am writing about energy. So anti has the least energy, right? And is the most stable conformation. Now let's plot this as an energy diagram. So in the energy diagram, on the vertical axis, we have potential energy, as well as on the horizontal axis, we have dihedral angle or the degree of rotation. So since we started with NT, where the dihedral angle is 180, so I'm starting with 180 first. And when I rotated this, the conformation I got was partially eclipsed conformation, which I'm showing here, right? And if I rotate this by another 60 degrees, so this this hydrogen is going to come here, methyl is going to go there. So this conformation is Gauche conformation, right? And if you rotate this, what you will get, a fully eclipsed, right? And so on. So we have moved from anti to fully eclipsed, and then the again Gauche, again partially eclipsed, again anti, right? Now energetically, fully eclipsed is the most energetic. So we can see that it is here. It's the most energetic, while anti is the least energetic or the most stable. So we can see there, right? The energy difference between anti or anti and the fully eclipsed is 19 kilojoules per mole. So if we take the energy of the anti conformation to be 0, then the energy of the fully eclipsed conformation is 19 kilojoules per mole, right? The energy of the partially eclipsed conformation is 16 kilojoules higher than the energy of anti or anti. For anti, if the energy is taken to be 0, then the energy of the partially eclipsed is 16 kilojoules higher than this. The energy of Gauche conformation, which increases because of these methyl interactions, they are quite close to each other. This energy is higher by 3.8 kilojoules per as compared to the anti one. So while in case of propane or ethane, all the eclipsed conformations were degenerate, while in the case of butane, they are non-degenerate. There is fully eclipsed, which is of highest energy, and there are partially eclipsed, which are lower in energy. So all the eclipsed conformations are not degenerate, means they are not of the same energy, they are of different energies. Two different types of energies or two different conformations are there. Similarly, for the lower energy states, we have two, anti and Gauche. So anti and Gauche, Gauche and anti. So staggered conformations are also not degenerate in case of butane, right? Now, if we look clearly, like I have drawn this in the expanded form, this is the anti conformation where the methyl groups are as far apart as possible. So if you look at here, so there is nothing in the space of methyl groups. So that's why anti is stable, more stable or the most stable of all the conformations. While in case of Gauche, although it is also staggered type of conformation, but the methyl groups are in the space of each other leading to strain, leading to strain, torsional strain, right? Now, if we focus on the fully eclipsed conformation here, this is the fully eclipsed conformation where methyl is eclipsing methyl, hydrogens are eclipsing hydrogens. The energy of this system when calculated experimentally is 19 kilojoules per mole, right? From the previous videos, we talked about propane and ethane, and we know that hydrogen-hydrogen eclipsing conformation, hydrogen-hydrogen eclipsing interactions contribute to 4 kilojoules per mole of energy increase. Torsional energy increases by 4 kilojoules per mole when hydrogens and hydrogens are eclipsing each other. Since in this conformation, we have two hydrogen-hydrogen eclipsing interactions, so total energy increase because of hydrogen-hydrogen eclipsing is 2 times 4. So 8 kilojoules per mole of energy has increased because of hydrogen-hydrogen eclipsing interactions, right? What does this mean? It means we are left with these interactions, methyl and methyl. And we know that the total energy of the system which has increased because of all the interactions is 19 kilojoules, of which these two contribute 8. So how much is the methyl-methyl interactions contributing? So methyl-methyl eclipsing interactions increase the energy by 19 minus 8, which comes out to be 11 kilojoules per mole. So methyl-methyl eclipsing interactions increases the energy by 11 kilojoules per mole. And this increases not only because of the torsional thing, but also because of the steric interactions. Steric as well as torsional both contribute for this 11 kilojoules. So this increase, which involves 11 kilojoules, that includes in itself the increase because of the torsional things, increase because of the steric interactions. I hope this clarifies the whole scene. So if you like the content, please do like and subscribe, and let me know if you have any questions related to conformational isomerism. Thank you.